we have a slight variation. What we have here is 1 minus q squared up to 1 minus q to the n minus 1. The last factor is 1 minus q to the 2n. So what it means is, according to this embedding process, for columns of length n, you have to insert them in pairs. But when you insert the columns of length n in pairs, your smallest part is odd. So we have a new partition theorem. You have partitions into distinct parts, and you insist now that the smallest part is odd. Split these partitions according to the number of parts, parity of the number of parts. This split is equal except at the perfect squares. I looked into the literature and I couldn't find this theorem. It's a very mild variation of Euler's theorem. It's embedded in Ramanujan's last notebook. But as I said, the point here is how many people have actually looked at the combinatorial statements coming out of Ramanujan's last notebook. But now there is something more. Ramanujan's identity has an E, a parameter A in it. So what is the meaning of A? See, like a Jacobi triple product, this has got a parameter in it. Euler's pentagonal numbers theorem does not have a parameter. So the parameter must mean something. So what is the meaning of this parameter? So now here is my theorem. It's actually quite a deep theorem because the identity is deep. Okay, so take partitions into distinct parts and insist that the smallest part is odd, like before. Now you look at the gaps between the parts. You see, I always love to look at gaps and put weights. Okay, that's one of the standard tricks I use. So I look at the gaps between the parts. Now, if the gap between the parts is 1 or 2, my weight is A. If the gap between the parts is 3 or 4, my weight is A squared. If the gap between the parts is 5 or 6, it's A cubed and so on. And it's always nice for the weight formula to be multiplicative, because that's when you get lacunarity by cancellation. One factor is 0, you can get 0. Okay. So the weight of this is the product of the weights of the gaps multiplied by -1 to the number of parts. There the parity comes. That's my weight. And now here I have a theorem. Take partitions into distinct parts where the smallest part is odd. Count these partitions with these weights. Sigma pi is some of the parts. Okay. So when I say sigma pi is n, that means partitions coming of this type of the number n. Sum these weights. You get 0 except at the perfect squares, and the only thing that survives is minus a to the power of k. So it's this fantastic cancellation going on, but with the parameter a. So this is the first time a refinement of Euler's pentagonal numbers theorem with a parameter having lacunarity was found. So now I want to give you proofs of these results. Okay, so to prove these results, we're going to use the Jacobi identity that Ramanujan employed. So here's what we're going to do. Let me first prove the simpler theorem without the A. I'm taking partitions into distinct parts where smallest part, oh by the way, this is sort of the opposite of Nathan Fine. Nathan Fine looked at the largest part being odd. I'm looking at the smallest part being odd. Okay. So now, look at that. Maybe the smallest part is 1. All parts are distinct, bigger than 1. Parity, so this is 1 minus q squared, 1 minus q cubed, etc. Smallest part could be 3. All parts are now bigger than 3. Smallest part could be 5, etc. So this is a very straightforward expansion for that generating function. Now, I want to show that that is equal to this. Alright? I factor the full product out. This is the Euler pentagonal numbers theorem product. I factor that out. And when I factor that out, I have these finite products at the bottom. 1 minus q, 1 minus q, 1 minus q squared, 1 minus q cubed, up to 5 and so on. Right? And I want to show that that is equal to this series with the squares. Now this is the same as, now I use the Jacobi, special case of the Jacobi triple product identity, where I say, if I had this as minus infinity to plus infinity, then I will have this. So I have cut off the 0, k equal to 0 term, and I have 1/2 of it. So that's that. And I want to show that that's equal to this. Now, come down. So, divide by q infinity. So I got to show that this is equal to that. Another little game that I always play is, I love to calculate the odd and even components of functions. I think this is a good pastime. It has served me well in these. Some interesting things have come out. Not just in calculus for hyperbolic and sine h and cosine h, but I do it in Q series. Alright, so here's what we do. Look at the generating function for unrestricted partitions. That's that. That's the series. Think of this as a function of z, and now ask, what is the odd part of z? You can look at the series and immediately write down the odd part of z as, odd part of the function, as this series. Or you can look at the product and you can write the odd part as that. And now I put z equal to 1, and that is precisely this, which proves the special case of Ramanujan's identity. So this is, and I liked it because Ramanujan himself, in treating Nathan Fine's thing, even though